Okay. Anybody have any questions about anything we talked about last time? Yes.
Um, are you doing the Wednesday labs? Like, are those going
This
this week
week?
and next week?
No, no labs the first 2 weeks.
Okay. So,
Um, if you would like to come to lab and ask questions or whatever, I'd be happy to
all right.
do that. But I'm not giving any new labs.
Okay. I'd like to talk to you about possibly switching to the Wednesday one.
Okay, sure.
Okay. Thank you.
Um, and so you're in the Monday one now?
Yeah.
Oh, okay. Actually, I mean, unless it turns out to be a problem because it gets really lopsided for some reason, like everyone wants to be in Wednesday or everyone wants to be in Monday, just come to whatever lab works for you. You can even do it like a different lab every week if you want. Um, if so, yeah, let's just assume it's going to work. It usually seems to work fine.
Awesome. Thank you.
Yeah. Any other questions? All right. So last time we just pretty much talked about the structure of the course and what kind of math you need. Now we're going to get into physics. Um, and the first thing we're going to talk about is units and unit conversions. So any kind of measurement that you take in physics, maybe any kind of scientific measurement, has units attached to it. So all physics quantities first they have to be measurable. And they have to have units. For example, if you're asked how fast you're driving, like saying 42 isn't enough, you know? Although someone, I have 42 in my notes. I don't even, that's just totally random. And someone's like, yes, that's enough. That's the answer to everything or whatever, like from that movie. But you know what I mean? There's 42 miles per hour is very different than 42 centimeters per year or something, you know? So speed equals, I'm going to make it 37. That's not enough. It needs to be 37 miles per hour or 37 light years per month. Or dot, dot, dot. And we're going to need to be able to go back and forth from one unit to a unit of measuring the same quantity. So like if we're given the length of something in inches, we need to be able to express it in meters, for example. And so that's what I'm gonna talk about first. Every unit can be expressed as a combination of three. You can think of these as like the fundamental units, the fundamental quantities. So the first one is length. And that can be meters, feet, inches, miles. I'm going to put light years on here just because we're only going to do like one or two problems in this class that involve light years, but just for sounding smart at like cocktail parties or whatever, it's good to know that light years are a distance. A lot of people treat that like it's a time, but if like a year is a year, you know, like a light year is the same as a mouse year, you know. So a light year is a unit of length. It's how far light goes in a year. Then the second of these three fundamental units is time. That's going to be measured in seconds, hours, days, months, so on. And the third fundamental one, the last one, is mass. That is kilograms. This is sort of funny, but this is another thing that, like, on a bathroom scale, you usually have a kilogram setting and a pound setting, but kilograms and pounds actually aren't the same thing. Pounds are a measure of force, kilograms are a measure of mass. And you can relate mass to force if you assume a certain strength of gravity. So scales have that conversion because they're assuming that you're using the scale on Earth, you know, like that's a pretty reasonable assumption most of the time. But if you take a bathroom scale to the moon, it'll tell you you have your mass is some number of kilograms. It'll be totally wrong. Where am I going with this? So if I'm going to list out the different units of mass, kilograms is one. Pounds is not another one. Instead, anybody know what the imperial or like American system of mass units is? Pounds is force. It's grams is the same as this. It's just kilograms and grams. It's called slugs. No one ever uses it, but like really bathroom scales should have a kilograms slugs conversion. And so when I say that everything can be expressed as a combination of these three units, like as an example, and you know, we haven't talked about what any of these things are yet, but 1 Newton, and that's a unit of force, is actually, you can think of it as 1 kilogram times meter per second squared. So it's sort of a complicated combination of those units, but anything, you know, any unit you can think of can be broken down into a combination of these things. Volts, amps, joules, all of those you can write as combinations of those three fundamental units. And when you express a measured quantity, when you give a measured quantity, think of it as a number times the type of unit. So the number times the unit. For example, think of 25.6 meters as being the number 25.6 times the unit of 1 meter. And then when you do calculations involving these quantities, you treat the units the same way you would treat like an algebraic variable. So when these quantities are used in calculations, treat the units mathematically just as if they were algebraic variables. You know how when I I do these videos and I post the video in the PDF. Someone came up to me, it was like 3 years ago or something, and was like, could you, you know, it would be really nice. Could you post the PDF before class? So, because that'd be nice. I could take notes on it, you know? And I'm like, I'm writing it in class though. I don't know how to do that. Okay, so an example here is, so say your calculation is 10 meters times seconds divided by 5 meters. So what if the m's and the s's were algebraic variables? You'd be able to cancel those m's, right? And that's exactly what you do if those are units. So you end up 10 divided by 5 is 2, and you're left with 2 seconds. Okay. In this class, we'll almost always do our calculations in SI units. People tend to just call it SI. The SI is stands for a French thing, but you can think of it as Standard International. This is these are the units that people in every country except the US, I believe, use primarily, and it's used more and more in the US too. But in a lot of engineering applications, you still use the American units, which were originally called the British imperial units, that are like length is feet, time is seconds, and mass is slugs. But we're going to use SI units where length is meters, time is seconds, and mass is kilograms. And then using these, you can come up with a whole bunch of other units that are going to come up as the semester and the year go on. Like newtons are going to be the unit of force. Joules are the unit of energy. Pascals are the units of pressure. It goes on and on. Volts. Okay, so in this class, what I would recommend you do, and what I'm always going to do in calculations, is if I give a problem that's in some other kind of units, like say a distance is given as 50 miles, the first thing I'm going to do is convert the 50 miles into however many meters that is. And then I'm going to do all the calculations in SI units. Because to me, if you always do things the same way, it's easier to avoid mistakes. You know, it's not wrong to do it all in miles and whatever time units and mass units you're given. In the end, you could get the same thing, but I would recommend just always taking your starting values, put them in SI units, and then work with them in SI units. Okay, so to do the conversion into SI units, for example, how many inches are there in 3.5 feet? The idea is sort of simple. We know, let's say, relationships between numbers of units. for example, we know that 1 foot is equal to 12 inches. Okay, and since those two are the same quantity, 1 foot over 12 inches is equal to 12 inches over 1 foot, and it's just equal to 1, right? If you divide something by itself, you get 1. 50 divided by 50 is 1, right? Negative 20 divided by negative 20 is 1. So it's the same thing with these. These are, we know these two things are the same, excuse me, are the same distance, 1 foot and 12 inches. So this divided by this has to give you 1. And if you multiply anything by 1, no matter how it's expressed, you don't change the value fundamentally. So we're going to take our, what did I call it? We're going to multiply our original quantity by one of these fractions, one of these versions of the number 1. So in our example, our original quantity is 3.5 feet. And we're going to multiply that by 12 inches over 1 foot. Because we're thinking of these units as algebraic variables, the feet cancel. And you end up with 42 again. I'm stuck on that 42. 42, the only thing left after the feet units cancel is inches. Okay. And by the way, just to save a little time, I'll always write this as, so here's how I would write this. That line separates the numerator and the denominator, like in a fraction. And instead of writing all the parentheses, I'm just going to make the splits between the things I'm multiplying with a vertical line. Okay, so I'll write it like this. This means the same thing as that. We have 3.5 feet and 12 inches in the numerator and 1 foot in the denominator. These cancel and you get 42 inches. Anyone have any questions yet? Okay. So here's a question. What if instead, so this all worked out great, multiplied by 12 inches over 1 foot. What would happen if I multiplied by 1 foot over 12 inches? Uh, 1 foot over 12 inches. So we'd have 3.5 feet multiplied by 1 foot over 12 inches. In this case, nothing cancels, and we get a value of 0.2916, repeating, feet squared per inch. And there's actually nothing wrong about that. I mean, this really is a valid unit for length. You could do your measurements in feet squared per inch. The problem is that's just not what we're looking for, right? The question asked you to express it in inches. And in this case, we didn't get inches for our answer. So what you want to do is always multiply by the fraction that cancels the unwanted units. Bless you. So in that example problem, the unwanted units were feet. We had it in feet, but we didn't want that. We wanted inches. So I wanted to multiply by the fraction that canceled with the feet that were already there in our original quantity. Okay, so like in our original, feet was in the numerator. So we need the fraction that has feet in the denominator so it cancels. Okay. Okay. Now here is another example. I'm just going to do a few examples. Each one is going to bring in some new thing that I haven't done yet. So say the next thing we want to do is convert 46,000 seconds to days. And we're going to do it two different ways, okay? First, we're going to do it the easy way. Like say we had a table in front of us or Googled it or whatever, and it said 1 day is 86,400 seconds, okay? But then after we do it this way, which really is just the same as the example I did up here, the second way I'm going to do it is I'm going to say, well, I don't know how many seconds there are in a day, but I do know that there are 60 seconds in 1 minute. And I know that there are 60 minutes in an hour. And I know that there are 24 hours in a day. Okay. So the first one of these, we're going to start with this original quantity of 46,000 seconds. That's what we want to convert. And we're going to multiply by either 1 day over 86,400 seconds, or we're going to multiply by 86,400 seconds over 1 day. Which one do we want in this case? Right. That's right. Because the unwanted quantity here, the unwanted units are seconds. So we need seconds in the denominator of our fraction so that it cancels these. So 1 day over 86,400 seconds. And now the seconds cancel, and you end up with 0.5324 days. Okay, so that's doing it in one step. That's part A. But now for part B, we're going to have to do it in 3 steps. We're going to first have to convert from seconds to minutes, and then convert from minutes to hours, and then convert from hours to days. And you can do it all in one fraction. Like you don't have to, well, let's do it. Come with me. So our original quantity is 46,000 seconds. We're going to use that first fraction to get our answer in minutes. Do we want 1 minute over 60 seconds or 60 seconds over 1 minute? Yep. 1 minute over 60 seconds. And now if you canceled those, you see that the number we would get is in minutes. And now we want to go from minutes to hours. So do I want 60 minutes over 1 hour or 1 hour over 60 minutes? Yep. So 1 hour over 60 minutes. and the minutes cancel. And then the last step, we want to go from hours, which we would have if we stopped here, to days. So we're going to go 1 day over 24 hours. So the hours cancel. And you're left with units of days. Okay, there's no other units in there. And if you take 46,000 times 1 times 1 times 1 divided by 60 divided by 60 divided by 24, you get the same thing we got with the other approach, 0.5324 days. Yep. No, I'm not going to talk about significant figures in this class. I'd say yeah, just don't round off too much. I would never take points off for how much you round off, I don't think. I don't know. That's another one. Like, maybe you could figure out a way to get a point off if you tried, but it would have to be like pretty egregious, you know? Okay, so here's another example. Convert 61 miles per hour and that means miles per hour like this, even though it's written as mph, into meters per second. Okay, so how are we going to do that? Well, basically, we're going to have a couple of steps in this calculation. One of the steps is going to convert the miles into meters, and then the next step is going to convert the hours into seconds. So given that, let's say the conversion factors that we know is the 1 mile is equal to 1609.344. So if you ran the mile in track in high school, it really was 1,600 meters. You were 9.344 meters short of a mile, but you might have like stumbled and fallen on the ground over a distance of like 9 meters, and then you did go a mile, you know. But there was actually a like super good runner, one of the best runners ever in Minnesota. He ran for Burnsville High School in, I think he was a senior in like 2007 or something. And in high school, he ran under 4 minutes for what we call the mile, but it wasn't the mile. And that extra 9 meters like means that he would have, it was like painfully close, but like just over 4 minutes for the mile if you do the conversion. Anyways, who brought that up? Okay, so we're given that 1 mile is 1609.344 meters. And the other thing we're given is that 1 hour is 3,600 seconds. Okay, so we're going to start with our original quantity of 61 miles per hour. And when you have these combination units and you have one thing in the numerator and one in the denominator, make sure that you put the one that's in the numerator, the miles in this case, in the numerator with the number, and the one that's in the denominator should be, you know, in the denominator of the whole fraction. You're gonna put the number in line with the units. Okay. So I'm first going to use this first conversion to convert miles to meters. Do we want 1 mile over 1609 meters, or vice versa? Okay, so we want 1609.344. I wish I would have said, if we could go back in time, I would say maybe after you finished the mile, you vomited 9 meters. That would have been way funnier. And then it's like your vomit went a complete mile, but you didn't. That's what I'm saying next time. Okay, so 1 mile. And now we're going to multiply it by something that converts the hours to seconds. So this one's a little different because the hours that we're trying to cancel are in the denominator. So this time we want the hours of the second conversion fraction in the numerator and the 3600 in the denominator. So 1 hour, 3600 seconds. And now if you do all those cancellations, the miles cancel, the hours cancel, and you get a value of 27.26 meters per second. Any questions about that one? Okay, there's really only one other tricky thing that can come up with these. And that is that sometimes in these combinations of units, one or more of the units are going to be raised to an exponent. So, like for example, let's convert meters per second squared into yards per minute squared. Given 1 meter is equal to 3.281 feet. 1 yard is equal to 3 feet. And 1 minute is 60 seconds. Okay, so the thing that's different here is this seconds is squared. So when that happens, in your original quantity, write the original quantity. We have the meters on top. On the bottom, we have the seconds squared. And I would recommend just writing it out. Instead of seconds squared, write it out as seconds times seconds. And that has to remind you that we have to cancel. You know, if you add meters over seconds to the fourth, you'd have to write the seconds to the fourth as seconds times seconds times seconds times seconds. Okay, we have to cancel each one of those. So first I'm going to go from meters to yards. So I'll go 1 meter over 3.281 feet over 1 meter. And then 1 yard over 3 feet. So if you look at the cancellations here, the meters cancel, the feet cancel, and the units of length that you're left with are yards. That's what we want. And now we have to convert each of these 2 seconds to minutes. So we have 60 seconds over 1 minute, but that only cancels one of these. So we have to do it again. And now if you look at what units are left, you have yards on top and minutes times minutes on the bottom. 9.81 times 60 divided by 3 gives you 38,640 yards over minutes times minutes, and I'll just write that now again as minutes squared. Any questions about that? Does anybody know what 9.81 meters per second squared is? Yeah, that's 1g. That's the acceleration of gravity for something that's in free fall on Earth. And so this is also the acceleration of gravity, just expressed in units you don't see very often. But if you were doing a calculation of like an object falling, an object in free fall, or, you know, projectile motion, trying to calculate the trajectory of the vomit. I'm going to keep coming back to that one. There's still a lot of meat on that bone. Then you would use this number in that calculation if you wanted your values in terms of yards and minutes. Okay. Let's do one more example. And actually, on this one, why don't you, I'll give you a second, see if you can think through it, talk to the people next to you, especially if you get stuck on it. If you get an answer, compare it to the answer of the people next to you. See if you can make sense out of this one. It's a little bit different. It's sort of like, it's a conversion problem. Like the math is just the same, but that math is kind of hidden in the way the question is asked. Okay, so say that you have a cubic meter. So you have a big block that is a meter long in every direction. And say that it's made up of these little cubic centimeters. So you can imagine taking a cubic centimeter and stacking them up carefully until you have a big block that's a meter by a meter by a meter. So the volume of this big block is 1 cubic meter. How many cubic centimeters does it take to make that big block, given that there are 100 centimeters in 1 meter? So just take a minute and see if you can think through that one. And I'm gonna do this a lot, like just take a little break from lecture. You're gonna work on something together, look at each other's answer, you know. So get used to it.